Okay, chapter 6 is about gas, states of matter, and energy. This is a little bit of a shorter chapter. So solids are going to have high density, definite shape, and they're not going to be able to be very, they're confined to their shape. They can't be really, their shape can't really be altered. So they have small compressibility. When we heat, they don't really expand. The particles stay close together. And like we talked about, particles of a solid are usually pretty close together in space. Liquids, their particles are a little bit farther. They also have a high density. They have an indefinite shape, meaning that they will take on whatever space that they are in. They are able to be compressed more than a solid, but still small amounts in comparison to gases. And they will expand upon heating, only a small amount, but again, larger amount than a solid would. Gas, their particles are all over the place in space. They have a very low density. Again, they have an indefinite shape, meaning that they will take on whatever room or volume that they are being confined to. They have a large compressibility. We can confine gases down to a very, whatever volume we want it to take on. And if gases were to be heated, they're going to expand. So first, talking more about specifically gases is talking about the units of gases. So the units of gas can have multiple different units. We can measure in atmospheres, millimeters mercury, or torr, right? And so this question is from your OWL question 16, and it's just a matter of converting between these different units of pressure. So pressure applies to gas, and it's a force that is exerted on or against an object by something in contact with it. So typically it's measured in torr, but again, like it can be measured in atmosphere, millimeters mercury, or torr. So this problem is telling us that a barometer in the lab is reading 743 millimeters mercury, and they want us to express this in torr and atmospheres. So they tell us the conversion that every 1 atmosphere equals 760 millimeters of mercury and 760 torr. So if we wanted to get in from millimeters of mercury to torr, we'll start with what we're given, multiply with the bottom being what we're trying to get out of, and then the top being what we're trying to get into. And we'll use this relationship here where 760 torr is equal to 760 millimeters of mercury. So if we're multiplying and dividing by the same number, you probably know we don't really need to type this into our calculator to figure it out, but it's going to equal the same number that we started with. So 743, but this time we are in torr. So you might have different numbers for your OWL question, but that is how to do the first one. Second one, starting with the same number, but this time we want to go into atmospheres. So we're going to multiply by what we're trying to get rid of. Or I'm sorry, multiply by what we're on bottom by what we're trying to get out of. and multiply on top by what we're trying to get into, and then fill in the relationship here, where 760 millimeters of mercury is equal to 1 atmosphere. So once we multiply across and divide by the bottom, we get 0.978 atmospheres. And since we started with three sig figs, we're going to end with 3 sig figs. So whenever you're multiplying by a set conversion factor, it doesn't affect the number of sig figs, which is really confusing. But I think I mentioned this in an earlier video. Once we get out of chapter 1, sig fig wise, usually just use how much you start with. That's almost a foolproof method to knowing how many sig figs to use. Because most of the time, and the problems that we're going to work on here forward, everything we're multiplying by are conversion factors, which have which don't contribute to the sig fig rules. So, gas laws. We'll talk about 2 specific gas laws, the ideal gas law and partial pressure gas law, or combined gas law, I'm sorry. But first, I wanted to talk about a general principle between both of these gas laws. And that's the relationship between pressure and temperature. So this might be kind of intuitive, but if pressure increases, so does temperature, and vice versa. If pressure decreases or temperature decreases, so does pressure. And so they have a direct relationship. So an example of this is if we had food with like a TV dinner, something that has that film on top where it's, you know, kind of clinked to the side. If we weren't to cut any holes in that and we were to pop it in the microwave for a pretty good amount of time, we're increasing the temperature. And if you notice, sometimes you'll either pop that plastic film or it'll expand into this little bubble, and that's because the pressure inside has increased. So that's my best example. I'm sure there's other examples, but that was just the example I came up with. So food in the microwave with film. So the relationship between pressure and volume. If pressure was to decrease, then volume would to increase, and vice versa. If pressure were to decrease, volume would be increasing. And so this has a inverse relationship. And so an example I can think of is a balloon. So maybe we put, 200 liters, I'm just making this up, of helium in there, right? And so if we were to put it into a appropriate size balloon, right? And then if we were trying to compress it further, the pressure would increase and it might end up popping. I wrote poop. I'm sorry, pop. That's kind of funny. So the pressure on the inside is increasing. Maybe if we were to put this into a different size of balloon, it'd be kind of deflated. Maybe we put it in too big of a size, and the pressure would be decreasing from what it was here. So the ideal gas law is not on any AL questions, but I do think it could potentially be on the exam. And so I wanted to give you just one example and introduce it to you. So the ideal gas law is this formula in which you can use pressure, volume, moles, temperature to solve. If you have any of these variables, you can solve for the other. And so it's PV equals nRT, where P is pressure, specifically in the unit atmospheres. V is volume, specifically in the unit liters. N is the number of moles, where mole is the unit. R is this constant value. It's always this. And it has this crazy units. You can think of it as being L times atmosphere over mole times K. And unfortunately, we're going to see Kelvin because T stands for temperature, but measured in Kelvin. So the only reason that this number works is because this random constant value here has the units that cancel out all the others. So in the ideal gas law, units are important. Units matter. So here's an example. So I put over here the ideal gas law formula and then what they all stand for, including that R value. Don't memorize the R value, that will be given to you. So given the following sets of values, calculate the unknown quantity. And so here it's wanting us to solve for volume. We know that the pressure is set at 1.01 atmospheres, that the number of moles is 0.00831, and that the temperature is 25 degrees Celsius. So our pressure is in atmospheres. Our volume, we don't know, but if we set up the formula accordingly, we know that it will output us our volume in liters. Moles is in moles. But our temperature is not in Kelvin. So if we remember to get to K, we need to do 273 plus whatever it is in Celsius. So if I were to add 273 to this number, I'm going to get 298 degrees Kelvin. So now we're in Kelvin and we're all set to use this formula. So the formula again, PV equals nRT. It's over here. So I know what P is, so I'm going to go ahead and fill that in. I'm solving for V, so I'm going to put it as an X. We know it's going to output us in liters. N, number of moles, which we are given. Then R, which is this crazy constant. I'm not going to put its units just because I'm lazy. And I know that since I have all my other units correct, it's going to cancel the units out. And then temperature in Kelvin, 298. So once I multiply all of these and then divide by this side, I am left with 0.201 liters. And so here I'm using 3 sig figs because everything else, the least amount of sig figs is 3 and everything else. So like I said, you don't have an OWL question, but please don't rule this out because it's very possible that it could be on your exam. So the next gas law I want to talk about is the combined gas law, which is in which we can compare the same species on both sides and compare how they will change if we change pressure, volume, or temperature. So this is very similar to the relationships I was trying to describe to you earlier, right? This is the formula in which we can go ahead and apply that principle. So let's think about a balloon, right? Let's say we have a really shriveled balloon. Maybe I know its volume is 4 liters and its temperature is, let's say, 25 degrees Celsius. 25 degrees Celsius is room temperature, by the way. Say I have another volume with, or another balloon with a smaller volume, but it's at the same temperature. They're in the same room. And I want to know how the pressure changes. Maybe I already know the pressure for this one. Maybe I know that the pressure is 5 atmospheres, and I want to know how decreasing the volume will change it. If I want to know the exact numbers, I can plug it into this formula. So with this formula, units don't matter as long as they're the same on each side. So as long as my volume, so let's call this balloon 1 and this balloon 2. So this would be my pressure 1, my volume 1, and my temperature 1, all being plugged in on this side of the equation. We'll call this balloon 2. So this is my pressure 2, my volume 2, and my temperature 2 being plugged in on this side of the equation. So as long as my units are the same on each side, so for instance, my volumes are both in liters, my temperatures are both in Celsius, doesn't matter what the units are. My pressure, if my pressure for 1 is atmosphere, I know that the formula, whatever number I get, should be atmosphere for pressure 2. So remember, this is comparing the same species, right? We're talking more, this formula is more about how does the same item change? So I talked about this being 2 different balloons. Really, we could say that this is the same balloon, but over time, right? So let's look at this as a practice problem. So this is from your OWL, and this is question 17. So nowhere in the actual problem does it say combined gas law, but when we read it, we can determine to use the combined gas law formula because it's giving us a whole bunch of different numbers. And it's asking us, it's telling us that this gas is compressed and asking us what the pressure is. So if we were to be looking at a similar question and trying to figure out to use combined gas law or ideal gas law, you'll be given number of moles or asked to solve for number of moles or something. The moles would be a cue to use the ideal gas law. Combined gas law, you're going to be having 2 of the same thing. So here we have 2 different volumes. We have 2 temperatures because it's telling us it's staying at a constant temperature. And so if you if you accidentally thought, oh, this is the ideal gas law, when you start to plug in the volumes, you'll realize, wait, I have 2 of them. I don't have 2 places for it. So this is a combined gas law problem. So just a reminder, the formula is PV1 over T1 equals P2V2 over T2. So let's read through the problem and determine what each of these values are. So I like to set myself up just a little chart here. So a sample of helium gas is at a pressure of 0.632 atmospheres. All right, well, this is the first pressure I've read. I'm just gonna assign it 1. This same gas has a temperature of 21.7 degrees Celsius. So I need to make sure I put that T with T1. And the same thing occupies a volume of 11.1 liters. So this is again going with 1. So now here's the change. If the gas is compressed, to a volume of, sorry, I jumped ahead there. If it's compressed at a constant temperature, right? So I can just repeat this temperature over here. To a volume of 7.84 liters, what is the pressure? All right, so now I have all my numbers and I know what to solve for. So it's just a matter of plugging all these numbers into this formula. So we need to make sure that our units are the same on both sides. They're both liters on both sides. They're both degrees Celsius on both sides. And obviously whatever P2 ends up being will be in atmospheres. So I'm going to go ahead and fill this in. So if it's the same temperature, a really easy way to do is just disregard this on bottom if they're the same temperature, and then go ahead and just solve the problem by doing 0.632 times 11.1 divided by 7.84. If you wanted to actually plug this into your, do it with the temperatures, it just gets a little bit more messy. So P2 equals 0.89, and I get 4, 7, and some other digits atmospheres. We're going to be rounding this to 3 sig figs because all of our given quantities were in 3 sig figs. So it's going to be 0.0895 atmospheres. All right. And so then the final slide for chapter 6 here is a phase change diagram. So we might have seen this before, or it might just kind of feel intuitive. But as we increase temperature, we change from the phases solid to liquid to gas. I want to point out that sometimes the temperature to get from freezing, from a solid to a liquid it's not just a magic linear gradient. We have to be able to hold that temperature and put in some energy in order to actually get to the liquid phase. So that kind of explains sometimes why as soon as we hit 32 degrees on the, let's say there's snow on the ground and you wake up the next morning and it's 32 degrees outside, it doesn't immediately melt. All the snow doesn't become immediately liquid, right? It takes a little bit of time, right? And that's indicative of this plateau here, where it takes a little bit of energy. So the sun has to shine just a little bit more in order to change. The same happens from the liquid to the gas phase. So some terms to know here too is that melting is when we go from a solid to a liquid. Freezing is when we go from a liquid to a solid. Vaporizing or vaporation is when we go from a liquid to a gas, and condensation is when we go from a gas to a liquid. Sometimes we can go, maybe the temperature changes really, really rapidly, and for holding for enough period of time, we can go from a gas to a solid, and this is called sublimation. The same thing can happen solid to gas, and this is called decomposition or deposition. I saw it written both ways. All right, so I just want to show you that graph. I believe this is kind of heavy in your Labster this week. All right, so that's the end of chapter 6. Chapter 6 is nice, short, and easy. We love that.